The perfect ingredients for a tornado. Tornadoes don't appear out of nowhere. They need the atmosphere to line up three key ingredients: moisture, instability, and wind shear. Moisture comes from warm, humid air near the ground, often traveling north from the Gulf of Mexico. Above it, cool, dry air moves in from the west. When the two meet, the warm air rises rapidly, creating instability. That's the energy that fuels thunderstorms. The last piece is wind shear, which means wind changes its speed or direction at different heights. This creates horizontal tubes of spinning air across the sky. When rising warm air tilts those tubes vertically, that's the first sign that rotation could begin. The birth of the supercell. When instability and wind shear work together, they'd form a special type of thunderstorm called a supercell, the most powerful kind on Earth. Inside a supercell, a strong updraft of warm air pulls those rotating air tubes upward, creating a huge spinning column known as a mesocyclone. The mesocyclone is basically the tornado's early form, a rotating updraft several kilometers wide that feeds on warm, moist air. As it strengthens, the entire thunderstorm begins to rotate. These storms can last for hours and are responsible for the most destructive tornadoes ever recorded. The rear flank downdraft, RFD. As the mesocyclone spins, a new force develops on the backside of the storm, the rear flank downdraft, or RFD. The RFD is a burst of cool, sinking air that wraps around the rotating updraft. As it drops toward the surface, it drags rotating air downward from higher in the storm. When that cool air hits the ground, it collides with warm, moist air rushing into the storm. This boundary between inflow and outflow tightens the rotation dramatically, the same way a figure skater spins faster by pulling in their arms. At this moment, the storm's rotation stretches toward the ground, setting the stage for a tornado to form. Birth of the funnel cloud. As rotation intensifies, a visible funnel cloud begins to appear below the cloud base. This funnel isn't made of debris. It's mostly condensed water vapor, the result of rapidly dropping air pressure inside the vortex. Where the pressure drops, the air cools and moisture condenses, revealing that twisting, ghostly shape. However, a funnel cloud isn't a tornado until it touches the ground. Once the rotating column connects the storm base to the surface, it becomes a true tornado, pulling warm air inward and upward in a powerful continuous cycle. The power inside the vortex. Inside a tornado, the physics become extreme. At its center lies the vortex core, where air pressure is at its lowest and wind speeds are at their highest. In the strongest EF5 tornadoes, winds can exceed 300 miles per hour, powerful enough to lift vehicles, strip pavement from roads, and tear houses from their foundations. Air at ground level spirals inward, then shoots upward through the vortex before spreading out again at the top of the storm. This constant circulation keeps the tornado alive as long as it has warm, moist air to feed on. The most intense winds usually occur near the surface, which is why the base of the funnel is often the widest and most destructive part. The tornado life cycle. A tornado doesn't stay the same throughout its life. It passes through three main stages: organization, maturity, and dissipation. Organization stage. The funnel forms and strengthens as rotation tightens. Mature stage. The tornado reaches peak intensity, becoming wide, fast-spinning, and capable of immense destruction. This is when it does the most damage. Dissipation stage. As the storm's warm inflow weakens, the tornado begins to narrow and lose energy. It often ropes out, twisting into a thin, graceful shape before fading completely. Some tornadoes last just a few minutes, while others can persist for over an hour, traveling more than 50 miles. Even short-lived ones can cause catastrophic damage. Tornado families and outbreaks. Sometimes a single storm doesn't create just one tornado. It can generate a family of them. As one vortex weakens, another may form nearby, often following a similar path. This chain of tornadoes leaves a nearly continuous trail of destruction that can stretch for miles. Then there are tornado outbreaks, when several supercells form across a wide region at once. One of the most historic examples was the 2011 super outbreak in the United States, which produced over 300 tornadoes in just 4 days across 21 states. These outbreaks happen when large-scale weather systems, like cold fronts or jet stream disturbances, set off multiple rotating storms under perfect conditions. Measuring tornado strength. To classify tornadoes, Scientists use the enhanced Fujita EF scale, which rates their strength based on the damage they cause, not direct wind speed measurement. EF0 to EF1. Weak tornadoes with winds up to 110 miles per hour. They can break branches, damage roofs, and overturn small structures. EF2 to EF3. Strong tornadoes that can destroy houses, toss vehicles, and tear down large trees. EF4 to EF5. Violent tornadoes with winds up to 200 to 300 mph. They can flatten neighborhoods, lift heavy debris hundreds of meters, and leave only foundations behind. Scientists use Doppler radar, drones, and mobile weather labs to study these storms in real time. This research has greatly improved early warning systems, giving people precious minutes to take shelter before impact. The core of tornado formation. At the heart of every tornado is a simple principle: nature's attempt to balance energy. Warm, moist air collides with cool, dry air, and the atmosphere responds by spinning that imbalance into motion. The true core of tornado formation is rotation, the interaction between rising air, sinking air, and shifting winds. When these forces line up perfectly, they feed off one another, forming a self-sustaining loop of energy and motion. Even with advanced radar and computer modeling, predicting the exact time and place of a tornado remains incredibly difficult. But every storm we study helps scientists better understand how these rotating monsters form and how to stay safe when they do. The future of tornado research and prediction. Even after decades of study, tornadoes remain one of the hardest weather phenomena to predict. But that's changing fast. New technology, from mobile Doppler radars to AI-based weather models, is giving scientists a clearer view of how tornadoes develop minute by minute. Machine learning systems can now analyze thousands of past storm patterns to spot the early warning signs of rotation, long before humans can. Drones and storm probes are also making a difference. These compact devices can fly or roll directly into dangerous storm zones, collecting high-resolution data on temperature, pressure, and wind speed near the vortex itself, something that was impossible just a decade ago. Researchers are also using supercomputers to simulate storms in 3D, testing how tiny atmospheric changes can trigger or prevent a tornado. All of this points to one goal: saving lives. The more precisely we understand the invisible forces that create tornadoes, the faster we can warn people, turning minutes of uncertainty into moments of safety. Climate change and tornado behavior. One of the biggest questions in meteorology today is how climate change affects tornado activity. Scientists agree that a warming planet increases atmospheric moisture and instability, two ingredients that fuel severe storms. However, the link between global warming and tornado frequency isn't simple. Studies show that the number of tornadoes each year in the U.S. hasn't dramatically increased, but their distribution has. Tornado Alley, once centered over Texas, Oklahoma, and Kansas, is gradually shifting eastward towards states like Tennessee, Alabama, and Mississippi. What's also changing is tornado clustering. Instead of a steady number of storms spread throughout the season, we're seeing fewer outbreak days, but with more tornadoes forming in short bursts. That means when conditions are right, the storms are far more explosive and unpredictable. As weather patterns continue to evolve, scientists are keeping a close eye on how rising temperatures, jet stream shifts, and humidity levels reshape where and how tornadoes form in the future, the mystery that remains. Despite all our progress, tornadoes still hold secrets. We know how they form in general terms: at the exact moment a tornado touches down, the split second when swirling air becomes a deadly vortex, remains one of meteorology's greatest puzzles. Some storms have every ingredient for a tornado and produce nothing. Others seem weak and suddenly generate powerful funnels. Tiny differences in humidity, terrain, or updraft strength might be responsible, but no one fully understands why. Even the structure of the vortex core is still being studied. High-speed cameras and radar scans reveal mini whirls and multiple vortices spinning inside one main funnel, a chaotic, mesmerizing dance of air that science is only beginning to decode. What's clear is that tornadoes are both awe-inspiring and humbling. They remind us that, despite our technology and models, nature still has the final word,